This is Project 6, video number 2, the one in which I coded up. Let's see if fire up the editor here. Edit. Get it so that you can see it. I want to go function. I don't have to return anything, so nothing equals, and then my function name, I'm going to plot frequency, plot frequency versus time. Just call it plot frequency. And then I've got two arguments: the distance away from the track, I'll call that D, and the frequency of the source, I'll call that F. I'll end this function, tab over. I think I want to try saving it, and make sure I'm in the right spot. Yeah, Project 6. Save plot frequency.m. Alright, then I think I want to refer to this, and so I got to initialize some variables. Delta x, x0, f, and v. I might call that the speed of sound in air, v sound. So delta x, I think I'll just call it dx, equals, what was it, the velocity? Oh no, equals 1,000 meters. So I just put a semicolon there. X0 equals 500 meters. That's where it started out. V sound, I know is, oh, the frequency. F equals 440 hertz. Let's make sure that is, yeah, 440 hertz. A real train whistle has a bunch of different frequencies and an infinite set, really, but even among their frequencies with a great deal of amplitude, the center of each distribution, there are several of them, like about 5 different ones, each one a different musical note. But for purposes of this problem, our train is carrying a frequency generator that creates a single frequency sound. Alright, oscillates at one single frequency. It's an idealization. And what did I have? Oh, V sound equals 343 meters per second. That's 4 items. Let's see if that's how many I had here. 1, 2, 3, 4. Yeah. And then calculate delta t. I'll call that dt. Maybe total time. Yeah. Otherwise I have to explain what it is. So total distance equals 1,000. Alright. Total time equals total distance divided by the velocity of the train, vt. It's not frequency that's given, or that's provided by the user. It's vt. Alright, the frequency is just a fixed value that was given in the problem, so it's not something that the user passes along. I mean, I know I read that once before, but 2 arguments. The first argument being the distance that the person is from the track, and the second argument being the speed of the train. Speed of the train. Okay. So divided by Vt. t, and then t, set up our time array. So times, I think I will keep the array name simple, t equals, and then linspace 0, comma, total time, comma, see what looks smooth with 100, and then what? Create an array of positions using that. X0 is equal to x is equal to x0 minus v sub t times t. X equals x0. X0 exists, so I can use that. And then minus vt given by the user times t. Alright. Now I don't need a dot star here because I'm multiplying every element in the array by just a single number, and then I'm subtracting that result from a single number. So x is going to be an array of 100 values now. And then at each position x, I think I got to calculate what the speed is, the component of the velocity toward the person. I don't know how I got that straight green line there. Let's try. Yeah, there we go. VTP is equal to that. Alright. Let's see if I can do it. V toward, I think I'll call it. V toward the person, the velocity, the component of the velocity toward the person is equal to the velocity of the train times x divided by square root of x squared plus d squared. Alright, this is where I do have problems. This is an array. You can't square an array like that. Not a one-dimensional array like we got, but to do it on an element-by-element basis, we put the dot. And now I'm dividing the array x by an array, whatever the square root returns. So I need that there. Here I'm just multiplying by a number, the speed of the train, so that's fine. Okay, so I get an array of 100 v toward values that way. And then, well, I'm already ready to create the frequency array. F prime is that, v minus vtp on the bottom. So F prime equals v divided by v minus v toward, and then all that times the original frequency, but this is v sound, the velocity of sound in air. I'm pretty sure that's what I called it. Up above, put a semicolon there. V sound, yeah, 343 meters per second. And then plot t comma f prime. Alright, let's see what we got wrong with that. I'll save it and try running it. But I did a lot of typing, so it's got to be something wrong. Plot frequency. And I want to try it with my test case, 0, 50. So I think I got problems with forgetting to put a dot. So let's check that out. Yeah. this is an array. V sound, well, V sound isn't, but my denominator is, because V toward is an array. So V sound minus V toward, that's no problem. Multiplying the whole thing times an F, well, that's going to happen later anyway, but so let's do the division first. I want to divide just a pure number, but by an array. So I'm dividing by an array. I got to say, do that on an element by element basis. So you divide this pure number by each element of the array that's in parentheses here in turn, and then each number, then you get an array. That gives you an array right there of 100 values. And then I'm multiplying that array by just a single value. Usually extra parentheses make things harder to figure out rather than easier, or to read, but I think in this case, to make it clear that I'm multiplying everything by F, I prefer it that way. I could put the F out front, and then math ambiguity, or if it is an ambiguity to anybody, would go away, but this way it looks more like the formula that you see on your formula sheet, with F being afterwards. So I think I'll leave it that way. Alright, so it's that whole quantity. I think that's all that error was about, so I'm going to save it. Try running it again. This time I got no error messages. And I got frequency. Yeah, 515 is the number I remember. It looks like it's going down to about 380. I think it was 385, 515 to 385. For my check case, let's see. Yeah, 515 to 384. So that actually looks good. I got that false zero issue. So with graphs, if you have to, you have to. But let's see how bad it looks without the false zero. That is, make this axis run from 0 to 550. People tend to automatically think that where the two axes intersect is 0, 0. It's not always the case, but it might throw away too much information by making it a false zero, but I want to try it anyway, by making it a true zero, like making it so that the axes really do intersect there. So it's okay the way it is, but I'd like to see if it's worth it. I'm going to go wide limb. It's open, and then this thing takes a 2-element array, and I want it to go from 0 up to auto, I think. I forget how you make it so that it's automatically chosen. I don't really want to mess with the upper limit, so I'm not sure whether that's going to work or not, but save that. Might have to look up YLM. No, automatic doesn't cut it. And yeah, I'm going to go ahead and pause this video and look that up. Well, I'll at least go help YLM. And gets that mode can be set to auto or manual. Let's try auto in quotes. So not sure it's really saying that either, but it seems like it's worth a try. So Control S and then run it. MATLAB, hit. No, still didn't like it. So set axis Y limit mode. Alright, something to do with axes. So I'll go ahead and see if I can find this with the video pause. Alright, I'll let you in on the next thing I'm going to try. This YL gets the Y limits. So I'm going to try that Y limits. And then I'm guessing this is going to be a two-dimensional array, the Y min and the Y max, and I'll put that in there for the second one. You know, what it automatically calculated it should be. So this might not be the simplest way, but Y limits equal Y lim. And I think I'll leave the semicolon off, so if this doesn't work, I get to see what's going on. And then Y limits of 2, that is the second element of the Y limits array, I think is going to be what the upper limit was. So all I'm doing is saying keep it the same as what it was. In fact, if I put Y limits of 1 right here, then it would be identical, except change the lower limit to 0. But I want to get that printed out the first time I run it, just to see if what I think is happening. So boom, boom, no error, and look at that, it actually changed. Oh, okay, the Y limits was up at 520, and it changed it to just changed the lower limit, so it's still at 520. I thought it was at 550 before. But okay, I think I didn't let you get a chance to see what that looked like. I recognize that puts the whole graph pretty near the top of the page, but I think it's okay. I think that's better than having a false 0. I think I'd have preferred 550 up there. But the thing is, well, let's see. We're not going to have a train going greater than 300 meters per second. Suppose I just set. Let's try that. I think I'll set that to a specific value, so it'll always be the same for all my graphs, or at least I'll try it. So let's see how high the frequency would be if the train were going 300 meters per second. So I'm limiting there, so it's the theory falls apart at 343 meters per second. But let's see what it's like at 340. If it's less than, if it's too much, I don't want to do it. But so we'll make that 300 meters per second. Run it. Gets up to 4,000. So that's a lot. Let's actually take a look at that figure. So that looks nice there, but if I set the upper limit to 4,000 in the first place, so let's try that at just 4,000. Then Control S saves it, run it. Messed up. Need the bracket. Control S it again to save it, run it. So of course this one looks fine, but might not see much of anything if I go with the old one. 0 to 50. Yeah, I think it's hiding everything. So I'm gonna go with choosing that one automatically. We'll let the computer decide what that is. So Y limits of 2. I think I can make it so that that doesn't get printed out. Try that again. Save it, and so no false 0. And we've already seen if it if we got a really fast train. 300. Yeah, plus I'm not really putting any limits then on the code except for the one that's built in. You can't have it going faster than the speed of sound. Alright. So there. It looks quite nice. Alright. I actually want to play around with it at 100. So, yep, looks good there. Now, let's move the person away from the track. Move him 15 meters back from the track. And see what we got. Alright, so cool. They're pretty close to the track, so it starts out as if the train's coming straight at them. I guess I should have looked at the numbers with the should have 100. So about 620 down to looks like 350 to 620. Alright. So then move it back away from the track. Still doing that. So this is, the train's so far away it's essentially coming straight at you even though you're not quite on the track. But then when it gets close it starts mattering. And then at one point you're hearing the actual, the same frequency that the oscillator's vibrating at, and then it dips down below. Okay. If I move away from the track pretty far, what happens? I guess now I'm just thinking from let's go 250 meters away from the track. So a little bit hard to hear it, but I'm expecting it changes a little bit more slowly. By the way, I'm printing stuff out here. I better take care of that. It looks like I left a semicolon off someplace. Yeah, there it is. So I was printing out 100 values of X. Save that. Next time, hopefully not. Yeah, there it is. It's never moving that much directly toward you. And then it gradually, nor away from you, because you're so far away from the track. It's always moving directly toward that point on the track that you're closest to, but when you're off at an angle like that, the component of the velocity toward you is not that great. So the upper to lower frequency, the difference is not as great, and the change is more gradual. Let's say 100 meters away from the track. And going at 100 meters per second, that's like 200 miles an hour. Alright. I think that's pretty cool. So it's acting like it's coming straight toward you there, but then it's more the decrease is more gradual. And then when it passes you, it's still pretty sudden, during these few. And it's taken 10 seconds. Does that make sense? I said 100 meters per second, and we're going 1,000 meters. So yeah, 10 seconds times 100 meters per second would be 1,000 meters. So that part checks out. Okay, I think I actually got the code working, and I've gotten a chance to play with it a little bit. I think it's pretty cool. The frequency changes with time, and that should actually do it for Project 6, video number 2.